I hope my screen is visible. My voice is audible.
Yes, ma'am.
All right. So we are going to do today is reinforcement learning. In last class we have done with GANs. So anybody GANs? Can anyone do a quick recap about GAN? I can say that we have two components in the GAN. First is what and second is what. Anyone? In today's quiz, you are having questions on GAN as well as on reinforcement learning as discussed in the previous class, and it is also having negative marking. So focus and for the GANs, uh, I know because in one lecture it's very difficult to, it's a lengthy topic, but still something you might remember about this. So we had two components. First one,
Generator and the discriminator.
right? First is generator, second is discriminator. Okay, what does generator do? We have real images, we have fake images. So what does a generator do? Generator tries to generate images that looks like real, and discriminator tells that whether it's a real or whether it's a fake image. Okay, discriminator tells generator whether it's real and whether it's a to communicate with each other. Discriminator always keeps on telling generator that what that you have generated fake image, you have generated fake image, until generator learns and until it generates the real image. This process goes on, and while when generator generates a real image that looks like almost like a real 100% approximately, or maybe 99, 98, something like that. So when generator gives a good accuracy for the real images, so discriminator tells okay this is real, and then this goes off and only generator is left which is trained. All right, so this is overall GAN. Now, today we are going to study about reinforcement learning. Okay, in reinforcement learning, we are also have a look at, we are going to look at Markov learning. I'll explain these terms because it's too much to, so many terms are there, but for the reinforcement learning, I'll tell you basics. Okay, in basic, you don't have to, because it's a very very lengthy topic. This reinforcement learning is a very deep and lengthy topic, although, but what we are going to cover today is just basics, and just remember only the basic terms that I'm telling you. Okay, no need to get into much depth because otherwise it's gonna take so much already. Okay, so let's discuss. So I've taken these slides from Stanford lecture series. I can share YouTube link to you as well if you want to go through it. Stanford deep learning lectures are there, and you can visit that, and all the lecture slides are taken from that. Okay. Okay, so let's start. So in reinforcement learning, we have seen in initial lectures also. One lecture was there where I have just introduced what reinforcement learning is. So what reinforcement learning is? So we have seen supervised, we have seen unsupervised. Now let's see reinforcement. In reinforcement learning, scenario is a bit different. Scenario is just like real world. Okay, suppose this is I'm just giving example. This is earth, Suppose in some other universe there's another Earth, okay? So the person who is on that Earth and the person who's here, so environment for that person is he will look his Earth according to whatever the scenario. So that is his environment, and my environment right now I am explaining. So this is my environment. So similarly, suppose we have a computer system and some game is running over there, which is, let's say, Mario, okay, and we have another computer, there's another game running that is also Mario. But the Mario 1 and the Mario 2, these are different, and the environment for Mario 1 is different, and environment for Mario 2 is different. So basically, it's a relative term. So when I'm talking about environment, this means wherever the agent can move. So I can move to this place. So this is my environment. So Mario 1 in computer 1 will move in its own space. So that is his environment. Mario 2 in second computer is moving in his own space. So that is his environment. All right. So this is environment where agent can move particularly, specifically. All right. So agent is the person who is taking action, who is doing something. Okay. So in a Mario, what happens is he wants to reach to the final step by killing all the distractions in its way. All right. So he wants to reach to the goal. So agent is basically the uh, action doer, basically who is doing actions, and he has certain goals fixed that he wants to reach some final destination or like that. Okay, so that is agent. Now in step one, what happens is, so this is how reinforcement learning work. It's basically uh, environment where something is happening and we want to simple in a simple life also. Suppose you are standing somewhere and you want to go somewhere, so you have multiple paths to go to that place, to go to your destinations. All right. So this is done basically through machines, basically through learning. Okay, instead of how do we do that in real life? We check all the possible scenarios. Suppose I want to go from a to place B, so I'll check first path is this, second path is this, third path, and I will check all the possibilities, like how much money it's gonna take, how much time it's gonna take, right? So everything according to that, and then I'll decide which path I'm going to, which is the shortest path and which is the best path. Okay, so this is reinforcement learning is all about. Here, the agent is basically deciding that how he wants to reach that goal, and in the optimal way, best way possible. All right, it should not take the longest path, and even if it's a longer path, it should have certain other things. Okay, so this longest shortest is decided by reward. Okay, so what happens is, first of all, in step 1 we have agent. Okay, so environment gives the agent a state. Agent was having some environment. All right, it was in some state S naught, initial state S naught. He was standing somewhere, and so he takes some action. He can take action A1, he can take action A2. There are multiple actions he can take. All right, so suppose he takes action A2, so he moves to another environment, like suppose he has killed in a Super Mario. Suppose Mario has killed some ducks and he has jumped into some tunnel, or he has moved to some place. So that is so his environment, because he has moved into tunnel and he has moved to certain location. Now his environment is changed, and his environment at that present is the location which is like suppose he's jumped into water. So his now is water. Okay, now from that environment, what happens is that environment gives uh, at that point environment gives a reward. Okay, that you have saved your life, so this is your reward. Is yes, you have saved your life, you have done the correct action, or like that. So environment will so step 1 was agent was having some environment. It takes some action, it moves to second environment, and then at that environment this gives some reward, and also it gives next state. Okay, so it gives reward was that Mario was not dead, you have saved a life and you have moved to next environment, next state. All right, so this process goes on. Mario jumps to some next level and so on. Okay, so this process goes on until it reaches to the final destination or final place where he wants to settle down. All right. So this process is reinforcement learning. This whole process of learning, and environment gives a reward every time. Suppose Super Mario is dead somewhere, so reward was zero or something like that. So okay, so this reward is given every time that agent takes action. And so two things happen basically every time agent does something. First is reward is given, and second is it moves to some new state. All right. So this is a simple example of reinforcement learning explained in terms of games. All right. So this is step one. So we have a environment, it moves to some new state and some action is performed, and then environment gives some reward, and update its state because it has moved to a new state. All right. So example we have seen the cardboard problem. So in a cardboard problem, the reward is that this pole should not it should stand upright, it should not move get down in a horizontal way, it should stand upright. So every time we are moving this card to some position, from one position to another, this pole should be upright. So whatever action we are taking, and that is we are applying some force on the card, so that is the action we are taking. And every time we are taking that action, our reward would be that yes, our pole is still standing, it's still upright. All right. So similarly, robots. So state is basically the angle and the position of the joints. Initially, it was at some position. Initially, the robot was at some position, and then some action was taken on that robot. Okay, and some torque was applied, some force and force were applied on the joints, and then a robot moves to some other position, and that other position okay, yes, robot has done what it was meant to do. Okay, so this was a simple example of robot. So everything utilizes games and all these things utilizes reinforcement learning. Okay. Similarly for games and all, so any game, chess or any other checkerboards, all right. So this is the overall idea of the reinforcement learning. Now let's see how do we write this mathematically, because it's theoretically looking okay. It's theoretically too much that we have agent, we are moving somewhere, and we are getting into new state. So let's see how do we mathematically write this all. So this Markov decision, basically Markov decision process gives us a way to write this. So initially we have five things. Okay, so when you are explaining a problem, so a problem of this reinforcement learning, you must explain these five things. First is you have a set of possible states that from one position you can move to other position. So all the set of possible states. A is the set of possible actions that you can take. Suppose you were at simple chessboard, you were at this position, so action could be either you can move here, here, or here, depending upon the type of agent that was here. Suppose agent was some, he can jump to some this position, so you have three positions, this position and this position, and so on. All right. So action is what are the possible actions that you have. And R, so R is the distribution of reward given a state and action pair. Suppose the position of this uh, agent that was here, it moved from here to here. So and it killed the king for this chess. Okay, so this was so this position basically made him lose this game. All right. So what was the reward? So reward was negative, -1, win, lose, like that. All right. So reward is basically what is the output uh, that is given depending upon the action that agent has taken. Yes. Question. Um, Okay, all right. So next we have transition probability. So transition is basically moving from one state to another. So this agent has moved from this position to second position. So this is the transition probability. Then discount factor. This is important. So discount is nothing but the suppose in future because this state from this state it will move to some other state, then it will move to some other state over here, it will move to some other state, all right. So there are multiple states. So discount is basically uh, di- discount decides the how device decides the reward that we are going to consider. Suppose it is moving from this position 1 to position 2, and my discount at 2 depends upon because depends upon all the future discounts. Suppose it can move from here to here, and there are three possibilities where it can move, all right. So discount basically checks that how much weightage I want to give to that reward of moving from position 2 to position 3, okay, or moving from position 2 to position 4. Okay, so discount decides, okay, moving from position 2 to position 3 was very important, so I'll give more discount to it. All right. So discount basically decides how much reward I want to give uh, while moving from one state to another. All right. So simply, so we
Ma'am,
start. Yes.
why do we need discounts separately if we have an action state pair which gives us a specific reward?
Yes, because there are multiple, because it's not a future state. This is from 1 to 2, and then we have 3, 4. Okay, so this state moving from 1 to 2 is dependent upon the environment at over here, and environment over here. So all the future environments are, dependent upon this movement. So discount is basically, so we can, what we can do is we can give high discount to this one, little bit lesser discount to this movement, little bit lesser discount to this movement. All right. So it's basically because this movement from 1 to 2 is more dependent upon 2 to 3 than others. So discount basically is out of all the possible actions that it can take, which one is more important and which one is in future, basically in future, not right now, but in future. I can give discount point 1 to this one, point 8 to this one, while calculating this 1 to 2. Okay. Mute your mic, whosoever it is. Okay. Uh, we start at time t is equals to 0. Okay. So agent selects some action, and then what it does is it samples a reward from all the set of states and actions. So he was here, he has so many actions and so many states. So state 1 was there, state 2, 3, 4, and 5 were there, and action 1, action 2, action 3, action 4, and action 5. So many actions were there. All right. So out of these all state action pairs, so environment samples reward for whichever action it has taken. Either it has taken this one, so it will give some reward. All right, and it will tell uh, this to move to next t plus 1. Okay. Then agent receive rewards and moves to next state. All right, so this process is repeated until, so final, what is my final goal is final policy is basically to maximize, this is by not you, uh, final policy is to maximize the cumulative discounted reward. That means the final reward, uh, whatever actions it is taking from 2 to 7 and 2 to somewhere here. So all the sum, so cumulative for all the set of rewards is should be maximized. Okay, suppose it's taking longer path to reach 8 from this, and it is taking shorter path from here, so I'll give maximum reward to this one, minimum reward to this one. Goal is to select from either this path 1 or this path 2. From both these paths I can reach my goal, but I'll give my aim is to select that path which maximizes the reward. All right. So this is my final objective. So this is they are showing an example where aim is to move to this one or this one. If I am here or if I'm here or here or any position, so my goal is to reach to these gray points. Okay. So suppose if I'm here at position A, and I want to, my goal is basically either I have to reach to this or to reach to this gray one. All right. So one way is either I can move to this direction or I can move to this direction. So we can see we are humans and it's easy to say that okay, this is the shortest path and I will move in this direction. All right. So but just wait a second. But for automatic systems, what okay, yes. So uh, what I'll do is if it's moving in this direction, I will give a negative something 0.8 something, and if it's moving towards the goal, I will say okay, I'll give it to some positive something, okay, 0 point something. Okay, so basically my goal is to I want to reach to my gray points from any position in a shortest way possible. Okay, in the least number of actions should be there. All right. So this is just example of a simple movement from any position. So in a random policy, what I have is, from if I have this position, I have four directions. Either I can go this way, this way, this way, or this way. I have four options. In optimal policy, we have a particular set, because if I go into this direction, so I will, there are chances I will not reach to my goal. All right, so I'll give this to negative marking or something like that. Uh, so negative marking is basically that I'm going to lose this game, or I'm not able to reach to my goal. So basically I'm just discarding set of possibilities from where I will definitely not get the shortest path. Okay, so if I am moving in this direction, this is definitely not give me the shortest path. So either this will give me the shortest path, this will give me, and this will give me. All right. So that is why they have only considered these three options. So this is my optimal policy. So what I want to do is I want to have some optimal policy for all the set of possible states that I have in my game or whatever, in my problem. Okay. So optimal policy pi star, I want to find optimal policy that maximizes the sum of rewards. So those rewards at every point, I want to sum them all cumulative, and then I want to maximize it. All right. So how do we do that? So let's see. So this is the formal definition. How do we do that? Of how do we do that? So this is a little bit complex equation, but if you have a look at it, this is the rewards. So, and this is the discount. Okay, discount multiplied by rewards. That is how much weightage I want to give to my each and every reward. All right. So for first reward, I want to give more weightage and so on. So so this is basically the sum of all the rewards in simple words. So expected sum of rewards. So my goal is to maximize the sum of rewards. All right. Given I choose this policy pi, so I have set of policy is the what you can say in simple terms, it's basically steps, what steps I'm choosing. Okay, so policy is, so I want to choose the best policy. Best means optimal. So uh, my goal is to maximize overall reward for the system. All right. And this is S naught is the initial state out of all the possible initial states. This is action out of given at any state st what action do I take, then at any state st what action do I take. Okay, out of all the possible set of actions. Okay. Then similarly for next state, uh, which next state do I get given that I choose this action in a particular state. So I had state st and I choose action at and I get to move to new state that was st plus 1. All right, so out of all these possible STs and ATs, there are many states and actions. Which one will lead to best optimal ST plus one? All right. So this is it. So these three are given to me, and my goal is to optimize this final policy. 5 star. All right. So let's see. So what we are actually doing is we have some state and we have some action and then we generate reward for it. Then we move to new state and then we do perform some action and then we get a reward for it. Then this process is repeated until we reach to our final goal. All right. So we have two things. First is value function. So value function decides how good my state is. So if I'm into present state, how good that state is. So if I'm moving from 1 to 2, if I'm moving from 1 to 3, so I must know that either 2 is better or 3 is better. So my present state is better or not. Okay, so if I am in 1, so it's right now it's not deciding that which state I want to move. It's only deciding that okay, 1 was better or not. Okay, so value function is basically the expected cumulative reward from following the policy from state S. So if from state S I choose to go to I choose this policy where I go to 2. Okay, if I choose this policy, so what would be my expected reward would be. So what reward do I generate at this one? All right, so this is so whether it's a so this decides whether it's a good state or not. So in a game if I reach to this one, so this reward will decide that it will make me win or make me lose, like that. Okay, so this is value function. So it is basically nothing but sum of all the rewards. Okay, future rewards basically. And next is q value. So q value is nothing, it is just uh, whenever so I have decided I have calculated the value function for the state 1, that either it can go to 2 or it can go to 3 है ना. So I have decided for 1 that okay, this was a reward. Now I want to know that if I'm moving from 1 to 2 or if I'm moving from 1 to 3, which one is better. So it is basically it depends upon basically action. For one, we are not talking about action where we are moving. We are just talking about the reward of this present state and in value function. And in Q value function, we want to know that if I take some action A, so what would be the uh, reward then? If I take this action, what would be the reward then? And if I take this action, what would be reward then? All right. So this is the sum depending upon the action A. All right, so same equation is there, discount and reward. So this t is basically because in future what are the possible uh, at every time what would be the possible discounts and rewards would be there. So sum of all those. All right. Now Bellman equation is there. It is optimal q value function. Basically what we want to do is we want to find the optimal function which is the maximum of all the rewards. That is what we want to do. We want to maximize this value. So Bellman equation gives us a way to do that. So it is nothing, just simply saying the same thing in a different way, not in a different way. So what this looks complicated, but it is not actually. What Bellman equation is doing at every step, it is calculating the present reward if I was at state 1 and my reward was R, okay, and if I am moving to state 2, and if I'm moving to state 3, so it is saying that the my uh, optimal reward would be the reward for the present state plus the reward for the next state that I'm moving to. All right, so this is not complicated to understand. Why? Because definitely my present optimal reward depends upon what actions I take in future. All right, so my in future, if I decide to go to this two or three or any other state, so my reward at this present state is dependent upon what reward that I have plus uh, what reward that will generate if I take action A dash. Okay, if I select to choose action A dash, and I move from this S state to S prime state, S dash. All right. So it is nothing but so this equation is nothing. It is just saying the present reward plus the future rewards. Future rewards when I take some action A dash to move to state S dash. Okay, from S to S dash I'm moving, and it is just the sum of all those. Okay. So what happens in this is we are just at every state. Suppose I was so this was my diagram 3 and okay, so this was my state 1, state 2, 3, 4, and 5. So if I am moving from 1 to 2 and 1 to 3, please just give me a minute. Okay, so now I hope it's clear. थोड़ा सा मैथमेटिकल कंपोनेंट है, बट नथिंग, जस्ट आपको यू हैव टू रिमेंबर व्हाट इज एस, व्हाट इज ए, व्हाट इज आर, थ्री थिंग्स, एंड व्हाट इज पाई, पाई इज पॉलिसी. ठीक है, दैट्स ऑल, nothing more. And then fifth term is your discount. So these five terms you have to remember, and if you know these five, you know what exactly is you are doing. ठीक है, and we are going to discuss this in more detail in next lecture also, no issues. I guess so we are okay. I think we are running out of time, so let's stop this over here only. Okay. In next class I'll discuss how this is happening, how this all is happening. Okay, so let's stop and let's move on to quiz. There is a negative marking, I'm saying this again. Okay. Um, I'll make quiz available and you all can proceed. All right. So go to module 4 quiz for today's date.